mesh, and also we see the very fine mesh to resolve the boundary. In the STAR-CCM we call it prism mesh. Okay, so now we need to set up the solver, and which means what kind of algorithm we use to do the simulation. And in order to do that, we need to go to continue again, and once we did the mesh, there will be a physics folder be generated automatically, so we can open it. So on the physics we have models, which means what kind of model we are going to use. By default there is a 3-dimensional one, which means we are going to simulate the 3D flow. So we can double click this models folder, and we will have such a window to select the algorithms for the solver. So now we are simulating gas. We want to simulate gas through this backward physics step, or you can do liquid, doesn't matter. So we click gas. Once it's selected, we'll go into the right hand side in enabled models. Okay, and what type of flow algorithm? You can see there's a coupled and a segregated, and okay, it's only one choice. In here we just choose coupled, and you may wonder what's behind, what does it mean coupled? And it's a bit complicated to explain in here, but for our case, for this backward facing step flow, both should be okay. That's what I can say. And to start easier, and since we want to simulate the low speed, and we can do constant density, but it doesn't matter, we still choose ideal gas. So we can do, because it's very low speed we want to simulate, and we can set constant density, because at low speed the density of the air doesn't change. Okay, so and then it asks us about if it's unsteady or steady simulation. We want to do the steady. What is the difference between steady and unsteady? Unsteadiness means we want to see how the flow evolves in time, but in here we'll just do the steady. See the average flow field. Okay, and viscous regime, and there is either inviscid and laminar or turbulent. So in here we will choose turbulent. And now ask us about the turbulence model, and we can do this is Splat-Amaras turbulence model. It's a 1-equation model. We can do this K-epsilon model, which is a 2-equation model, which is quite standard also. And now there are more advanced models we're not interested now. Okay, so all the models has been selected. We can close. So this is a selection of the models. We've selected the models for the simulation or for the solver, and we can see all the options we made are listed on the models, okay, in physics 1. And we just mentioned there is air going through it, and air is a type of gas. So if we expand gas, you can see the air is chosen. And let's see what kind of parameters we have. So you have the density, and it's a constant value. If you have different density, then you can just change it, which is quite straightforward. And then dynamic viscosity, that's also constant, and you can also change if it doesn't match your parameter. Okay, so this is for the model. We can minimize it. And now what we're going to do is to set up the boundary conditions. And now it's opened on the regions And if we open the region folder, we will see the boundaries. In total, there are 6 boundaries. And so the inlet has already been changed earlier. So the inlet is called velocity inlet, and which allows us, this type of boundary condition allows us to set the flow speed. And outlet is called pressure outlet, and that's related with the algorithm, because for low speed flow, and the outlet pressure will be updated by interpolation from the interior point. Okay, and the top is wall, no doubt, and the bottom is also wall. We don't need to change by default. But Z0 and Z1, which are the two side walls, we don't want them to be wall, but we want it to be symmetry plane, and also the one is also symmetry plane. Basically, the flow is symmetrical towards these two planes at either side. Okay, and in this case, because I remember if it's taken as a wall, there will be prism layer, but now we've changed the boundary condition for Z0, that one, from wall to symmetry plane. So we need to update it. We don't need prism layer to resolve the near wall region, because they are not taken as wall. So we just update the volume mesh. Okay, so for now, the boundary type of boundary are set. We need to assign the numbers. And so, for example, for the inlet, we want to specify the inlet flow condition. And then we can go to the inlet, and we need to find the change of value. So it's at the end, a physics value for the inlet. Okay. Okay, in order to set the boundary condition, and for the inlet, we need to go to physics value. Just now I missed it. So we need to go to the physics value, and we can set the velocity magnitude. We can say, for example, for now, 5 centimeter per second, 5 centimeter per second. It doesn't recognize only meter. So then we can do 0.05, that's 5 centimeter per second. And there are some other parameters can be changed. Flow direction, if your flow is not normal to the inlet, so you can change to different components. Yeah. And for our purpose, we can assume the flow is parallel with the inlet, with the wall, so it's normal to the inlet plane. And for the, so now we are done for the inlet. And then if we go to the outlet, and basically there's nothing can need to be changed. Okay, so now what we do is we have set up the boundary condition. Now we need to do set the initial condition. That's to give an initial value for all the internal points. And the initial value, especially the velocity, need to be changed, because we know it's 5 centimeters per second. We can give such a number and then update, so only parallel towards the x direction. So for now, we've set up the case. We got the grid, and we have the boundary conditions and also the models. Now it's ready to go.